Hello everyone. We have one more session that we're going to spend on cryptography. I titled it the Diffie-Hellman protocol because that's the main thing that we do, but I want to first address a little bit more about our RSA protocol. So let me quickly review it. There will be also a quiz on it. So we have two public informations, N and E. And those N actually is built up by two secret information parts, P and Q, which are primes. So these are primes, distinct primes. I should make that clear, but I hope it's clear. And E has to be, E, there's a condition on E, there's another secret number that is P minus 1, Q minus 1, the product of these primes minus 1. And that is also secret, that has to be kept secret. And so what the condition is that E and N have to be relatively prime. So let me write it up. So where such that the GCD of E and N is 1. So that is a condition. And then there is a last secret component, which all can be calculated. The only thing you really need to know is capital N. To break the algorithm, if you know capital N, then I'll talk about that a little bit in a sec. So this is the decryption key, and it satisfies such that D times E is equivalent to 1 mod capital N, not small n. And then the coding, so a coded message is obtained from a real message by taking the eth power of that message and reducing it modulo n. Okay, so you see the two public this is the public information, this is the message the person wants to send, and this becomes a coded message that nobody can decode unless they have this D. And then the decode, so this is encryption or encoding, so this is the encryption, and the decryption happens to, so to get the message M, what Alice, assume that Alice is the one that sets this up. What Alice would do is she calculates this power modulo n. Okay, and you see in this calculation it is the coded message. The message, it's the code. The coded message itself can be read by everybody, right? It's the whole idea is that this is unsecure line. So Eve, the eavesdropper, remember, can read the message. She can just not figure out what the original message M was. C she can see, M she doesn't see. So in some sense M should also be read, I guess, but let's stick to not too much colors here. Okay, so I have to address now, why is this considered to be a good encryption scheme, and why is it therefore used so much? But there, of course, what the size of these things, one normally chooses primes. Let me see here. It might be that nowadays they have even sometimes this data. I'm going by what the book says. I didn't research what it has nowadays is, because computers are getting faster, so they can do better things. And so we have to kind of always make it a little bit harder for computers to find. So currently, I think perhaps it's, this is of 2010, the information, so 10 years later, it might be that our supercomputers can work faster. You take P and Q are primes of about 200 digits. That's quite a lot, of course. So the first question is then, so I wanted to address here, how is it feasible to set this up? And in fact, what happens is, not only are we using these RSA protocols, but each time you make this protocol is used, one uses different public key. But if you start reusing the key too much, then you again are at risk of being that somebody can crack the code, because if they know that, or at least they see that parts of the code, well, it is more vulnerable if you use the key too long. So the most safe protocol is to consider to always use a new key. So when you connect to, let's say, an online bank, the bank will tell you, okay, send me your password, or not necessarily a bank, let's just say a website, and this website has your password. You originally, when you enrolled, well, or even if when you enroll. So okay, let's look at this hypothetical scenario. There's a website and you want to become a member, you want to be, you have a login account for that website. So they ask you some information, your username, you propose a username, and then you propose a password. And they will store that password, and in the future, when you then want to log in, they will check your password with the one that they have stored. By the way, it just as a side note, perhaps for those that are a bit more interested in it, that is nowadays no longer the practice, because what is the problem is now, if that website has your password and the website gets hacked, then your password is out in the open. And this has happened in the past a lot. A lot of these websites are hacked, and so these passwords are available. And that is, of course, a situation you don't want. So what one instead does is you're not sending your actual password, you send what is called the hash of the password. And the hash, we have seen hash functions, and then hash, what it does in this particular case, I'm not going to go into details, is transforms your password into a new string of letters. In other words, it's another encryption, but it is a weird encryption in the sense that nobody can decrypt it. So the goal is not to decrypt it. Okay, the hash is basically a one-way encryption. You say, whoa, how does that work? Well, so okay, here's your password. You hash it with a particular hash code. There are codes that are I forget the names of these things. For people specialized in this, they know. You can look them up. You can actually go in the web and find the app or little applet that does it for you. Hashes for you, so using a certain hash function. The reason is that nobody can invert it, so you don't have to worry about it. So you hash it, your password, and that you send to the website. Now, the website has therefore a hashed version of you. So when you log in the next time, you do again the same thing. You use the same hash on your password, and if that hashed form matches what they have on record, they say, okay, this must be the original password, and that must be the original guy. Okay, again, because the chances that these things are the same by luck is impossible almost. So that is why they guarantee that if the hash matches, then it's correct. So they don't know your password, but they know how the hash of your password looks like. But even that, of course, has to be sent secretively. Otherwise, if the other people might then know at least your hash and can pretend to be you, right? Because then they would log in with your credentials and with the hash of your password, and the website would think, oh, that's the original user. So even a hash is not secure, and it's not the purpose of it. The only purpose of a hash is that the website itself doesn't know what your password is. It only can recognize that this comes from your password. Okay, but that is a detail that has nothing to do with this. I thought you might want to know this. So let's go back and let's ignore now this hash part of it, and let's say, okay, you have this password, you want to send it using RSA. So what the website then does is says, okay, use this N and this E. So it gives you the public keys. Now as I said, it cannot keep using the same, because otherwise people can crack this. So it generates this. How does it generate this? That's the point I want to come to. So it has to find two primes of about 200 digits. So what it does, it takes random primes, random numbers of 200 digits, and checks for whether they are prime. Now, in the chapter on Fermat's little theorem and so, we discussed about primality testing, and we noticed that it actually is it's not yet polynomial. We cannot do it really in polynomial time. So it is actually it's on the face of it, to 100% be sure that a number is prime, you have to it's an intractable problem. It's exponential time, but there are testings that use Fermat's little theorem or little variants of that, where you can what we have seen is called pseudo-primes, right? So I remind you, if P is a prime, so let me write this down. So Fermat's little theorem is P is a prime, then A to the P is equivalent to 1 mod P. And if you go back to the discussion, A to the P minus 1, sorry. that if you take p minus 1 over 2, that divided by 2 is taking a root, right? So then this should be plus or minus 1, not p. That's the consequence of Fermat's-Little theorem, but it's not hard to prove. Okay, so and then you check this for various a's. Now there are numbers that pretend to be primes in the sense that for several a's they give this answer, plus or minus 1. But what one has figured out is that if you vary these various a here, and the test that I'm giving is not yet the best, you need a little bit more sophisticated than Format did, but it basically comes down to that. So you take various values of a, and each time it passes the test, in other words, the answer is plus or minus 1, you are more convinced that it's a prime. And it calculates actually the probability that you have a prime. So it is a probability test that after, let's say, if you do 100 of these, you test for 100 of these numbers, and each time it comes out plus minus 1, you are guaranteed that with an error of 0.0001%, this is a prime. And that is more than enough, because that, I mean, 1 in a million you are wrong, but okay, it might happen. If that happens, then later on the calculation will show that something is going wrong, But in other words, the chances that you have found a 200-digit number that passes this test, that it is not prime, is so small that we ignore it. And so we do the same so it does it to generate P, then it does the same thing to generate Q. So it has both generated P and Q, and that therefore now it has N, and that is now becomes a public information. Now it still has to choose little e and make sure that it is relatively prime with this N here. Okay, sorry, let me not circle this, with this N. So this e has to be chosen here, this condition. Now again, to choose an e to be 100% sure, I mean, what you can do is now, you just a random e, and then use the Euclidean. You don't want to factor things, because factoring this thing is also going to be extremely tiring, but we know there's a very quick way of finding the GCD of two numbers, namely using the Euclidean algorithm, which is in log time, so it is what we call very feasible. So so what it does is you take an e, and then it checks whether this is relatively prime or not, and if it's not, then it says, okay, let's take, instead of e, let's take then e plus 2. Because, of course, remember, these are odd numbers, so this is always an even number. Capital N is actually always a multiple of 4. So you cannot take e to be an even number, because then it's never going to be relative prime. So you just take random, or you take random e's. That's actually what they do. They take random e's, check odd e's, and check whether they have relative prime or not using the Euclidean algorithm until you find one, and then you say, okay, I got one. Here it is one. That's e. So it seems that behind the scenes, a lot of calculation has to be done. That's true. But they are all in log time, or all these calculations, everything that I said, this Fermat's-Little theorem, because it's modular exponentiation basically you have to do. This one is the Euclidean degree algorithm. All these are very fast. In other words, they can be done in a split of a second, even when we talk about numbers of size 200 digits. Right? That is, yes, you have to really understand this growth of functions, how much different it is if you have a logarithmic function or a linear function, or you have an exponential function. I go back to that chart where even for this size, 200 digits, you're talking about, if exponential time means, you cannot even phrase it in terms of the universe, because it's much more time than the universe would take. So finding these P and Q and E can be done in a split second, and you're almost 100% guaranteed. It's like with an error that is you can be ignored. It's like 1 in a trillion you could be wrong. You have a public key, and then you say, here you go. And in the meantime, of course, you calculate then this thing, which again we do by the Euclidean algorithm. I have seen this, and so we know that this is also something that it can be done fast. And then you take your password, calculate this, can be done very fast because it's modular exponentiation. C, you send C, and then the decryption goes also very fast because it's again modular exponentiation, and the website has your answer. So that is why this is a feasible protocol that is at the moment considered safe. However, we still don't know whether factoring a number into composite prime numbers is polynomial. This is an NP problem, a non-deterministic polynomial time. Remember, why is it NP? NP means that if I give you the two purported factors, then you can very easily check that they are the factors because you just multiply and then you see whether you get n. So that's a polynomial time you check. If you think that it's P and Q, you can check very easily. To find P and Q, that is considered at the moment intractable. However, that is not sure. So if P equals NP is broken, if P is in P, so this is vulnerable, or vulnerable is even a weak, too weak, it is broken, if P is NP. And the worst thing is that if the person that solves P and P most likely will find an algorithm to also do the factoring in polynomial time and therefore will crack the system. So we don't know that P is NP, right? But it might be. Another problem is it's vulnerable also, we don't know yet, by something that is called quantum computing. That is a very, cutting edge field that we don't have yet much power with. I mean, we know that actually in quantum computing we can factor, and in a very fast time, because quantum computing can sometimes do exponential time in polynomial time. That is, it's weird and that is very hard to understand, but that you need to take a more advanced course to understand quantum. You need to also understand quantum physics, of course, how that works. However, why is it at the moment not a problem? Because quantum computers are very hard to build. They require extremely delicate situation, and they are very volatile, a quantum bit instead of a real bit. And at the moment, the best we can do is factoring some number like 15 or something can be factored. There are your websites where you can go to where you can do actually quantum computers. You can use a quantum computer, but it is extremely little things it can do. Nothing compared to the 200 digits yet. At least what we publicly know, right? There is always the possibility that a secret NSA or the other intelligence agencies have been working on this and might know already what is P's and P, might know this, or might have a better quantum computer. Most likely they have, but nothing yet of it. It seems very unlikely that public companies have quantum computers that are perhaps can deal with, let's say, 2 or 3 digits, that all of a sudden somebody can build a quantum computer that can deal with 200 digits. That seems almost impossible. So at the moment, therefore, it is secure, but it is not 100% guaranteed that it will remain secure in the future, because quantum computers will hopefully, well, we don't know yet, but most likely will develop in the same way that regular computers developed. Go back to the early 60s and so, where computers were massive boxes, massive. I mean, they filled a room, and their power was less than, you had 100 of those were less than your iPad, your tablet or your iPad. So things will progress much more, and therefore cryptography, the field of cryptography, and also as the field of quantum computing, is a very field of a bit of high interest in. A lot of people are working that because they are looking therefore for better things, that once RSA is broken, or perhaps before it is broken, let's find a system that we know cannot be broken. And there is a belief that such systems must exist, and we'll show you one in a sec. Okay, now I want to add one more thing to this, is that this is one way using is sending a secret message, right? But it's also, there are other ways you can do. So suppose now Alice, so from Alice's point of view, so this is what we call, let me say what the topic is that I want to address here. This is called a digital signature. I don't know whether you have ever done this. For instance, this can, if you do Acrobat Reader, Acrobat Pro or something, or Acrobat Reader even, allows you to put on a document a signature that is a digital signature. It's not a signature that looks like your signature. It's not that. It is an encoded signature that identifies you as the unique person that has signed this. And again, it cannot be cracked. Or the idea is it cannot be cracked. So what it means is basically, if say now let's do from the point of view of Alice, right? So Alice has set this up, and Alice wants to send a message to everybody, but the people that get the message have to be sure that it comes from Alice and not from evil Eve or anybody else, right? How does she do this? So here is her message, and instead of sending that message, what she sends is she encodes the message. Well, I don't know. Yeah, okay, let's write it. Well, let me not use that color, because what she is going to do is she's not going to encrypt it. She's going to decrypt it. Although it is not an encrypted message, this M is an actual message, so it's not an encrypted message, but she pretends that it is. So she is going to decrypt it. Bear with me. So what she calculates is M to the power D mod N. What she would normally do when she decrypts, okay? And that she sends out. That is the C she sends out. And then that C she sends to Bob and company, to several people, or to just Bob, doesn't matter here. And everybody can see this C. So everybody sees the message. Sorry, no, I'm saying it. Yes, so everybody sees this message C. Yes. So of course, everything that has been sent is always considered to be insecure. Now, if Bob wants to know what is the message, what he has to do is now encrypt it. Right? So what he usually would do when he encrypts it, so he's going to take C to the power E mod N. And that will produce M. And why is this? Well, remember, why did this work? Why did this originally work? Let me write it here. If you take C to the power D, that is the same as M to the power E to the power D mod N. Yeah? But that is the same as M to the power D times E mod N. And this guarantees, by the Chinese remainder theorem and so on, that this is the same as M mod N. We did the calculation previously. Okay, so that guarantees us this, and therefore, that's how she decrypts. Now, but look, this calculation here, the powers D and E can be switched around. So let's see, if I do this here, what does this give? C to the power E. That is the same as M to the power D to the power E mod N. And now it's the same thing. Now you see that exponents have switched, right? E and D. Now this is D to the power E, but it is still the same. It's M to the power DE, which is the same as M mod N. So using the publicly available encryption key, you can actually get the actual message. So you say, that's not safe. No, it's not. The message itself is open for everybody to see. However, you now guarantee that it comes from Alice, because only Alice could have done this. Nobody else could have pretended to be Alice and sent a message, this particular message, this message M, because they would not know the D. They would not know how to make it look like that it's from her. And that's why it is considered a digital signature. And you can even do this. So this is in a case where we have the message itself is actually, everybody can decode it because everybody has this E available. But you can then, what one also does is you can then combine this to make actually send a message to Bob that nobody can know what the message is, and Bob is also guaranteed that it comes from Alice by combination of two different things. He can then make his own secret key to use that, and it's explained a little bit in the book, but let me not go there. I want to go to which is somehow the same as what I was trying to say at the end here. This is the Diffie-Hellman protocol. Diffie-Hellman protocol. And this is called a secret key exchange. And in some sense, I find this almost the strangest of all things that you can do here. So Alice and Bob want to create a secret key or a secret word, a password that only both of them know, and nobody else knows this word. right? That's a secret password. And I'll give you an application of it, how we can use that to actually encrypt them things. So remember, the whole idea of secure and encryption is that we assume that at any time Alice and Bob somebody is listening to what they're saying if they communicate. So at no time they can go secretly in the corner and say, here, this is my secret key, here, take it, and I'll take mine. Okay? We assume that this cannot be done. They are, like for instance, on different, somewhere else, far away from each other on the other side of the world, and they have to exchange this through public channels. So how can you make something secret where everything that you send is public? Weird, eh? Okay, so here is what we do. So they agree on a prime P. And when I say they agree on a prime P, that means they say, okay, guys, I'll do an example. So in my example, P is 41. So they send a text message to each other, let's use 41. So everybody knows that they're using 41. So perhaps I should make that in green, right? Everybody knows that this is the P. And they also agree not only on a prime P, on a root of unity, a primitive root A of modulo P, a primitive root modulo P. I remind you what that means. This means that if you take all the powers of A, that you get ZP. Well, you have to add 0 to it. So remember, this with a primitive root means that if you take a square, a cube, a fourth, a fifth, a set, you get all the non-zero numbers in ZP, right? That's what a primitive root mod A is. So they decide on that publicly. Everybody knows what they do. And then, so here in my example, now I'll talk about how to find a primitive root. There are, again, ways to do this kind of fast, to find a primitive root. So A is 6. I'm going to take A is 6. So you have to trust me that A is 6 is a primitive root of 41. I honestly, what I did, I went to Wolfram Alpha, and it allows you to do this. It says, what is a primitive root modulo for whatever param you give it, and it will give you an answer. There are ways of doing that, but I don't want to explain. This is beyond this textbook. Okay, so that's what you what we're going to use in the example. So now what they do is now they each secretly. So Alice is going to choose a secret exponent. I'm going to call E Alice. Sorry. Sorry. Yeah, no, what I'm trying to do here. No. So let's call it. I'll follow the book. Key Alice. Okay. And Bob chooses also something, and I'll call it key Bob. Key B. KB. So these are two numbers they choose without it telling each other what their numbers are, and nobody else. They just do it on their own. So in my case, Alice chooses 7, and Bob chooses 9. Okay. There's not really anything that they really, well, there's something that to do, but let's not discuss the nitty-gritty part of this. So that's what they do. Now, these are not the secret keys. Be careful. And this is the mistake people often make here. So what they then do. Now, Alice is sending to Bob. So Alice sends Bob the following. She takes the publicly available A. So yeah, let me put this. Yeah, so okay, this is my example, but sorry, this is the general case first. Let me first explain the general case. So Alice sends to Bob what? She takes the publicly available root A, raises it to her secret exponent, and then again reduces mod P. Okay, A and P everybody knows, but the Ka nobody knows, not even Bob. But he now gets this thing, and everybody knows this. Everybody sees this. Not only Bob gets to see this A to the power K to A, but even Eve sees this, okay? Because this is all publicly done. And what does Bob do? Well, it's exactly the same thing, but of course he uses now, Bob sends Alice using his key. So A to the the key of Bob, mod P. So, what is the secret key? Wait, we are not there now. So now the secret key. Oh, sorry. So that should be. Let me. So the secret key is the following. For the secret key for Alice, let me say it this way. So what does Alice do? She has to receive from Bob this. So let's call this now. Let's give these names to it. I call it C. Yeah, let's call this C, and let's call this D. I'm going to give them names C and D. So what has Alice received? Alice has received the number D. She takes D and raises it to her exponent. What is the secret key for Bob? Well, he takes what Alice sent her, that was the C, and raises it to his exponent. And of course, take modulo P. Sorry, that I hope was, we keep always doing this modulo P, right? So this is modulo P, and this is also modulo P. Now the whole point is that there seem to be two different numbers. No, they are the same. So these two numbers here, they are the same, and that will be our secret key K. Why is that? Let's figure out first why that is, but it's very easy to check. Well, let's calculate what is D to the power K, key Ka. What is D? Well, D was this one. Oh, no. Allez. But D is this one, so replace D by this, okay? So we get A, well, let me do everything in black, because otherwise I get A to the power KB, and now raise this to the power KA. Now you see what is happening? Again, the same thing that we had from before. This is A to the power KBKA, mod P. Now what is, sorry, that's the wrong letter. This is what Alice is, right? Alice is getting. What is Bob getting? Well, he takes C to the power KB. What is that? Well, C, using this formula, is A to the power KA, A to the power KA, and now we raise this to the power KB. But that's the same thing. Because, technically it's KB times KA. Oh, no, it's the same thing. It's the same thing, mod P. Well, not even mod P, they are even just the same, right? But we calculate mod P, so it has to be mod P, sorry, yes. So they are the same, and that is therefore the secret key. So be careful, that's often people don't go far enough in this calculation. In this calculation, these are not the secret keys, this is the secret key, okay? Because, remember, the C and D are public, okay? Now, these calculations are secret because only Alice knows this. Notice that Alice uses only her own key. When she sends it, she uses her own key, and when she receives something, she uses again her own key. And the same for Bob. So they each use only their own secret key. They're using this public information, sending also C and D publicly available for everybody, but nobody can crack this. Why? Because what you get is the key, the secret key is equal to A to the power the product of the two secret keys. Now, you can try to, how could you break this if you can find, so, okay, let's do this on an example and then we can talk about breaking this. So, okay, so everything is set up, so let's see, what does Alice do? What is C? That, remember, is the one that Alice sends to Bob. That is A to the power, I'll write it up, K to A, so this would be 6, publicly available 6, her secret 7, and this has to be done mod 41. Okay, now I do want you to do all these calculations by hand, but since I want to, I will do this in reviews and in homeworks, but here I want to go a slightly bit quicker to explain everything. So what is this? So I'm going to do this, I've just calculate this using Wolfram Alpha or some other tool, okay? 6 to the power 7 mod 41. Oh, no, okay, no, let me do it. Okay, sorry, I'm going to do it. It's not fair if I don't do it. Okay, so we have to calculate 6 to the power 7 mod 41. Fast exponential modular exponentiation, so we have to write 7 as, wait, no, not, sorry, I said the wrong number, sorry, I didn't mean 7, I meant 10 here. Let me, just for simplicity, make this into 10 here. So let me make this 10. Okay, no, not that it's much of a difference, but, oh. Okay, that is C, right? So what do you have to do? We take 6, so this is mod 41. We square 6, so 6 squared, that is 36. That's the same still. Then we square again, so 36 squared. Okay, let me get my calculator. Where'd my calculator go? Oh, there. Sorry guys, for some reason my calculator has disappeared on me. Where'd my calculator go? Oh, okay, got it. So 36 squared. That is 12. That is 1296. Divided by 41. That is 31 times 41. 1271. So plus 15, it seems. No, sorry, 25. Let me do this. I don't want to make mistakes. Yeah, 25. Okay, so right. So sorry. Yeah, we have to write 10 in powers of 2. That's 8 plus 2, right? So that's that. Then 6 to the power 8. That's all we need. We need 25 squared. That is 625. That is 15 times 41. And the remainder is 10. Okay? So what is this thing? 10 is going to be, remember, 8 and 2. So we need this number and this number. So 10 times 36. It's 10 times 36 is 360. And then 360 divided by 41 is 8. That is 8 times 41. That's 328 plus 32. Okay? So this is about 41. So C is 32. What is D? Well, D is 6, the same 6, but now to the power KB, right? And KB is 9. So now we're doing this for Bob, right? So 6 to the power 9. 9 is 8 plus 1. So you see, the good thing is you can use the same calculations here. So now we, let's perhaps do this in different color. Now I need 8 and 1, so I need this guy and this guy. So this will be equivalent to 6 times 10, that is 60, mod 41, that is the same as 19, right? Mod 41, just subtract 41 once from 60. Okay, so that's D. So C is 32, D is 19. And this sends us, so Alice sends this to Bob, 32, and Bob sends this, perhaps I should, you know what, I should call them, I don't know, what should I call them? I'm not happy with the choice of letter that I see, C and D. Okay, I'll stick with it now. So C is the one that Alice sends to Bob, okay? I should call that A, I guess, and D is the one that that Bob sends to Alice. Okay, so these are the two. Now what's the secret key? The secret key is, now be careful, you have to do it the right way. You can do it in two different ways. You can either calculate this or that, okay? So let's do the first one. So we have to take D to the secret power of so that's 19 to the power, this was the secret, so let's double check, right? Because I always get a little bit confused. Yeah, so you take the D that Bob sent her to the power, her secret power. So her secret power was 10, right? Yes, 10. And then again, we have to calculate this modulo 41. Now, this is not 6 anymore, so we have to do the same thing with 19 now. So, okay, let's do this. So here is 19. So 19 square, that is 361. So this is again mod 41, right? So divide this by 41, that is 8 times 41. And so subtract from that 361, that is 33. You could say this is minus 8. Let's do it that way. It's a bit easier. Minus 8. 19 to the fourth. That is minus 8 squared. That is 64. And that is the same as 23. Just subtract 41 from it. Okay, and then 19 to the power 8. That is 23 squared. Divided by 41. That's 529. That is 12 times 41, 492, is minus 37, plus 37. So minus 4, but let's not do this now here. Okay, so that's what we have, and what we know, what we need. Well, 10 power. The 10 power uses these things again, right? So no, that was the green one. So the green 8 and 2, we need this number and this number. I've taken the positive numbers here. So this is the same as 33 times 37, mod 41. So what is that? 33 times 37, that is 1221. That is 29 times 41. And minus 1221, it's 32. Huh. But that is weird. Sorry, let me double check here, because that doesn't make sense, I think. No, that's correct. Yeah, that is weird that this came out that way. But okay, let's see. What I need to check now, what I did was I took 19 to the power 10. But this should also be the same as taking 32, namely the thing that Bob receives and which he puts then to his secret power. Right, C to his secret power, and his secret power was where is the secret power? 9. 32 to the power 9. Let me double check here before I go on whether this is. Yeah, it is correct. So okay, so we have to do the same thing now for 32. Sorry, yeah. I'll make the chart here again. So 32, this is 32 square. Always mod 41 here, right? Always mod 41. So 32 square, 32 squared is 1024. So that is divided by 41. That is 24 times 41. It's 984. And then subtract that from, that's plus 40. I see. Which is the same as negative 1. Okay. So if we do now 32 to the power 4, that is just 1. Yeah, this is quite something. If you take this randomly, this cannot happen. But somehow we didn't take it random enough, and so this thing can happen. But it's okay. What's the next one? 32 to the power 8. Well, that's 1 squared. That's also 1. And what we need to do is, remember now we're taking the power 9, right? So this is 8 and 1. So we need these two guys. That's the first power and 8th power put together. That is 32. Now the point is that these two numbers here, that's the real point, is that these two values, whether you calculate it from the perspective of Alice or you calculate it from the perspective of Bob, you get the same number, and that's their secret key. That's okay. I mean, this particular number is a little bit weird because 32 has 32 to the power 4 is 1, and it might be more vulnerable to attack therefore. But in randomly chosen numbers, we won't have this kind of behavior. But still, even so, although she transmits 32, there's no reason to assume that the result also will be 32, right? So that is, it remains a secret key. Okay. Yeah, I don't know how I got so lucky to choose these two numbers that it came out that way. But there will be other problems, homeworks, and you'll see that's never going to happen actually, again, if you take it randomly enough. Okay, so that's the Diffie-Hellman protocol. So how it does is, it allows now, so this value that they finally found, perhaps I should circle it in red here, this 30, so k is 32 in this case. And again, I say it has nothing to do with the fact that C also happened to be 32. That is just luck, or kind of bad luck in some sense. But okay, so that's the secret key. And so I want to do one application. First of all, yeah, before I do this application, how is this safe? Why is this safe? So what you get, yeah, this is now not the best thing to do, of course, right? Okay, so let's see, why is this safe? What are the two information that people have gotten publicly? What is Eve? So now let's pretend to be Eve. I'll make Eve in purple. So Eve comes here and Eve looks at this and says, okay, let's see whether I can crack this. So I need to know, what do I need to do? Well, it's simple, she says. I just need to calculate C to the power. Remember, I should have written this down here because otherwise I keep. So this was, remember, this 19. This was, sorry, this was D to the power Ka, right? Yeah. And this was C to the power Kb. Okay, so she says, okay, let's look, she says, okay, let's take D here, 19, and I now just have to take this to this power, but she doesn't know that power. She says, that's a bit of a pain. So, but I know something, she says. I know that C is obtained. How is C? C is obtained as that power that I'm looking for of A. Right? So if I can write C as 6 to the power, so if this, remember, is 6 to the power Ka. Right? This is how C is calculated. Here's the calculation of C. Okay. So what she needs to calculate therefore is the log 6 of 32. So what Eve is going to do, so let's make Eve again in purple. So Eve says, I'm going to take the log with base 6 of 32 modulo of, let me erase this here a little bit because I want to write this out a little bit more nicely. Okay. Sorry. Okay, Eve, go ahead, Eve. What are you going to do? Okay, so Eve says, I'm going to do this. I take the log 6, or in general, of course, this would be the log of A. So let me write it like that. I'm going to take log A of the number C modulo the modulus, which was P, right? Mod P. And she says, oh, that's okay, because I know A, I know P, and I know C. I know everything. So here it is, I'm done. However, this is a discrete log, right? And the reason that we discussed about the discrete log was that it is, at the moment at least, intractable. And it is most likely intractable. I forget now the extending of this thing. To find the discrete logarithm of a number is, you basically have to run, and we have seen this in homeworks and so, to find the discrete log, you have to just calculate a squared, a cubed, a to the fourth, a to the fifth, a to the sixth, a to the seventh, until you hit your number. So this is an intractable problem. She has all the information that she needs, right? I want to point out that C is being publicly available to her, and P and A sure, because they were also publicly available. So everything is public, yet she cannot crack it. Now, if she would crack it, if she would be able to find it, remember, if this is Ka, right? That's what I'm saying. That's the whole thing she needs to build the secret key root. This is how the secret key looks like, D to the power key A. D is publicly available. So the only thing she has to calculate is this key A, which is something that is in some sense publicly available, but it takes forever to find it. So that's the beauty of this system. Yeah, everything is there. All the information that you need to crack it is there, but it takes you forever to actually carry out the cracking. Okay, and that is why this is secure, at least for now, considered secure. So I want to do one quick application that is not in the textbook, so pay a little bit attention to it. I'll call it, I came up with it. So I call it the numerical Vignières, what was that name again? Vignière, I always get this guy's name wrong. Remember we talked about him, the Vigenère, I don't exactly know how to pronounce it. Okay, the numerical Vigenère cipher. So here I came up with this. And what you do is, and let's do it on an example. Suppose Bob wants to send his social security number. His social security number is 0200202. That's his social security number. Just do something funny, okay? So this, let's perhaps make it a little bit less obvious. Otherwise, it's too much repetition. Well, no, let's do this. It seems like a very regular pattern, right? So what does he do now? So the Vignières, if you remember how it would work, is you had a keyword, and then you shifted the letters. So if in the regular Vignière, if you, for instance, take the word bloom, and you had to encode the word area, what you would do is you would take A shifted by B. Remember that last table I get? So you add 2, well, B has value 1, so you shift it by 1. R you shift by the value of L. I you shift by the value of O. A you shift by the value of O. And if there are more letters, you do even more shifting. Okay? Do you remember this? Go look it up. So we do exactly the same thing, but we now use this secret key that we have, 32. Okay, so we put 32, 32, 32. Oh, that's not a good thing. Okay, that's why I shouldn't have taken this number. Sorry. Yeah, let me take a different number here. Yes, let me take the social security number 21345688787. Okay, that's a social security number. No, that's too long for a social security number. Okay. This is the social security number. So we put 32, 32, 32, 32, 30. It's finished. And we just add mod 10 because our digits, right? So we work mod 10 to get a new digit. That is 5, 3, 6, 6, 8, 10, which is of course 0 then. 10 is 0, 10 is 0, and 10 is 0. Okay, that's how it works. So this is now the secret message, using this Vignière code. And my claim is it's impossible to break this unless you know the key K, because we saw that Vignière code ciphers can be broken, even Vignière ciphers, if you know the length of the code, because they're basically a combination of Caesar shifts, Caesar ciphers, where you're just shifting ciphers that we saw, and shifting ciphers can be broken by if you have a long text, you can do frequency, and you say this letter E comes much more frequent than this letter X, for instance, and that's why you recognize this E's. And once you have recognized that, you test it, and you can break the cipher, the Caesar cipher. Now, Vignière ciphers are combinations of this, and once you know the length of the cipher, you actually do this. You can break it in the same way. It's explained in the homework. But the problem is everybody knows the length of this particular cipher because, well, it is we work mod 41, so it can only have 2 digits, right? It could even have 1 digit, but okay, that would be a stupid cipher then, okay? So, but what you cannot do is the frequency analysis because it's just numbers. There's in social security number, I don't think any number that is more frequent than any other number. So, and you have only, in this case, he's only sending 9 digits. So there's no statistic frequency anyway, even if there were. Perhaps there are more zeros in a social security number than there are 9s. I don't know. I don't think so. But even so, that's just too little information. So this cannot be broken by because it's just 9 numbers. These are just these 9 numbers. And to find this, you have to, how would you find it? To decode it, well, instead of adding 32, so to decode it, you do 3, 2, 3, 2, 3, 2, 3, 2, and now you subtract. Oh, subtracting, right? Again, modulo 10. So that is 2, 1, 3, 4, 5, 0 minus 2, that is 8, 0 or 10 minus 3 is 7, 8, 7. And there we are, that's the original thing. So the encoding decoding is very simple if you have the secret key that you have exchanged between Alice and Bob. So this is a way for Alice or Bob to send the social security number safely without any anybody being able to decrypt it. Okay. I don't think this exists. I just came up with this. I thought it was nice to see an example specifically. So there will be no homeworks on it, but I won't ask it in the quiz, just as an extra problem. Right? It's very, very cute and very simple to do. Okay, so that's all for the lecture. It was a bit long. I'm sorry about that, but then we are almost done with our material of our course.